Hello, AP Chem students, and welcome to topic 9.3, Gibbs free energy and thermodynamic favorability. 9.3.a says explain whether a physical or chemical process is thermodynamically favored based on an evaluation of delta G. So Gibbs free energy is a measurement of the thermodynamic potential that is present in a system. It takes into account the enthalpy, the temperature, and the entropy of a system. So which can be seen in the equation that defines it, which, as you can tell from the formatting here, is on the equation sheet, which again this year will be as a drop down. This will be in the thermodynamics and electrochemistry section of the equation reference material. So in this equation, delta G standard is Gibbs free energy, also just called free energy. Delta H standard is enthalpy, T is temperature, delta S standard is entropy. So it's important to note that by using this equation, we only need to focus on the system, which is what makes it really useful. And as a notation, the standard symbol here, that little degree sign, what we are often used to seeing as a degree sign, but this case means standard, indicates that these are being measured in the standard state as pure substances with a concentration of 1 molar or as gases at a pressure of 1 atm. And they're measured at 25 degrees Celsius, but obviously you would not necessarily have to keep them at 25 degrees Celsius to use them in this equation. So let's talk about the meaning of thermodynamic favorability. So Gibbs free energy tells us if something is thermodynamically favorable or not. Now, if you go reading up on Gibbs free energy, you're often going to see the word spontaneous. And spontaneous is correct, and that is fine word to use. AP prefers the word thermodynamically favorable because if I say spontaneous, you probably think instantaneous, and that's not what it means. And we're going to talk about that in just a second. So we're going to use the terms thermodynamically favorable or thermodynamically unfavorable. So if delta G is negative, the process is thermodynamically favorable and occurs in the forward direction as written. If delta G is positive, the process is thermodynamically unfavorable and occurs in the reverse direction if that is possible given the quantities. If delta G is 0, the process is at equilibrium. So you can see this graphically. So if this is your reactants and these are your products, equilibrium is down here. So if delta G is negative, then that would mean that your products have a greater free energy than your reactants. And so that means that it's proceeding in the forward direction. If it's positive, you'd have the opposite. And if it is 0, you are at equilibrium. Okay, so keeping that in mind, we're going to continue to talk about free energy. My light is doing weird things behind me, my image. But we're going to talk about it in qualitatively first, evaluating your signs. So a couple of things to remember. First of all, number one, it says nothing about how fast the process is, strictly the direction. Something can be thermodynamically favorable and take thousands of years to occur, all right? So it says nothing about how fast it is. Again, that's why AP prefers the language of thermodynamically favorable instead of spontaneous. Second thing, if a process is thermodynamically favorable, its reverse process is unfavorable and vice versa. Finally, if delta H and delta S favor opposite processes, you'll have to look at temperature dependence. In other words, if their sign is the same, then you have to think about temperature dependence. Okay, so we've got a nifty little table here and a kind of a cute way to remember this. And so I want to show you this. And if I were you, I always kind of jot things down once testing has begun. And this is maybe one of the things that it's nice to jot down. So if you have delta H and delta S, and hang on, let me put the equation up here real quick. Okay, so by the way, I've got a cute little mnemonic for this. This is going home to supper. Yeah, kind of cute. So, all right, so if delta H is negative and delta S is positive, both of those are the thermodynamically ideal situations. So delta H is negative is an exothermic reaction. Delta S being positive is spontaneous in the forward direction. And so that means is increasing entropy in the forward direction, beg your pardon. And so let's talk about what that means, your symbols relative to 0. So delta H is less than 0 and delta S is greater than 0. And so then if you look at this as being like arrows on a number line, you can show that the arrows point to all values. And so then this is kind of cute because that's favorable at all temperatures. And that is driven by both entropy and enthalpy. In other words, both entropy and enthalpy are favorable in this system, and it will proceed regardless of the conditions that it is in. If we flip the signs, you can probably guess what's going to happen. So if your enthalpy is positive, meaning it is endothermic, and your entropy is decreasing, so it has less entropy, it's becoming more ordered, which is not what we would expect to happen spontaneously, then your delta H is greater than 0, your delta S is less than 0. And if we think about this as a number line for temperatures, there's no values, right? They point towards each other. There's no values at which this can proceed on its own. And so it is not driven by either entropy or enthalpy. So then as a side note, if you wanted this reaction to occur, you would have to do something to it, which we'll talk about more as we move later on into the unit. Now, I got ahead of myself. When you've got the signs being the same, so that means delta S and delta H favor opposite processes, then you have to think about temperature. So if delta H is negative, which is favored, and delta S is also negative, which is not favored, then in order for this to happen and be thermodynamically favorable, your enthalpy term needs to be larger because this needs to overwhelm the system. Okay, if you want to think about it that way. So here's the little memory aid. So your enthalpy is negative, which means it is less than 0. And your entropy is negative, which means it is also less than 0. So if we think about this as our number line, it is pointing that way, which is lower values of temperature. And so this is favorable at low temperatures. Now let me talk to you about that in terms of the actual equation and how you would justify this on the exam. So you would say that what you need is you need your T delta S term to be small, because what happens here is if your entropy is negative, then a minus is a positive. So you want this T delta S term to stay small so that your minus becoming positive does not overwhelm the negative value of your enthalpy. So this will be favorable at low temperatures. If you increase the temperature of this system, there will come a point at which it will no longer be thermodynamically favorable. You will reach equilibrium because at a particular temperature, you will reach equilibrium because your T delta S term and your delta H term will be equal to each other. And then as you continue to increase the temperature, then your system will be dominated by this unfavorable entropy process. So at low temperatures, it is favorable and is driven by enthalpy. Okay, so in a situation where both terms are positive, then again, of course, you can expect the opposite. So if enthalpy is positive, that means it is endothermic, which is not favored. But that means that if your entropy is positive, that means that your disorder is increasing, right? Your number of microstates is increasing, and that is favored. So we sometimes see situations like this, for example, with the formation of a solution. So sometimes a solution forming is endothermic, but the entropy increasing due to the solid and the liquid coming together to form a solution means that it is still a favorable, thermodynamically favorable process. So in this case, your enthalpy is greater than 0, and your entropy is greater than 0. So if we're on our number line, we're pointing towards this way. And so that is favorable at high temperatures. And in that case, it's driven by entropy. So the reason your temperature has to be high is that if this is a positive value, in order for Gibbs free energy to be negative, you would need your minus a temperature times your positive entropy to be a large enough term that this subtraction can compensate for your positive enthalpy. So I hope that makes sense. You might want to watch this part again and make sure that you fully understand, because I can almost guarantee you this question coming up on the exam. Okay, you can also calculate the change for Gibbs free energy. That should say Gibbs free energy, not just energy. So as with enthalpy and entropy, we can calculate the standard free energy change in exactly the same way that you've seen before. Now, I am going to assume that you know how to do this at this point, and so I am not going to show you an example of this particular calculation, but it is done in exactly the same way. Products minus reactants, you would multiply the values by their coefficients. We have done this with enthalpy, we've done it with entropy, and now you can do it with Gibbs free energy. Just like with enthalpy, so Gibbs free energy is closer to enthalpy in the way that we can manipulate it, because the value for an element in standard state is 0. And we can also treat it just like enthalpy in that we can do calculations with your delta G values in a similar way to Hess's law. So where you can multiply an equation, a step of an equation by a factor, and you can multiply delta G by that. You can sum two equations and you can sum their free energies. The reason we can do that is because, like enthalpy, Gibbs free energy is a state function, meaning it doesn't matter how you get there. You just compare the reactants to the products overall. And so we're going to use this factor of free energy again moving forward. Okay, so practice 3. So what is the boiling point of BR2 under standard conditions given the thermodynamic information about the process below? And so we've got BR2 liquid is going to BR2 gas. And so this, of course, is boiling or evaporation. And you've got delta H standard values of 31.0 kilojoules per mole and delta S standard values of 93.0 kilojoules per mole. So you notice that both of these values are positive. And so we need to think about that in terms of the thermodynamic favorability. So if you want to try this on your own, go ahead and pause the video now because I'm about to talk through it. Okay, so what I want you to think about is the fact that the boiling point, we're going to use the going home to separate equation. And your boiling point is the point of equilibrium between a liquid and a gas. And so at equilibrium, your delta G is going to be 0. And so we're going to use that, and then now we can solve for the temperature. Now, pay attention to your units and remember that you need to convert delta S into kilojoules, or you need to convert your delta H and delta G into joules. But to me, it's easier to convert one thing than two. So I always just, convert the delta S. Okay, so then I'm going to plug into my equation. And so at equilibrium, my delta H term is going to be equal to my T delta S term. And so using that fact, I can solve for T and get an answer of 333 Kelvin. And that is it. So what should you be able to do with this? Number one, there's quite a lot actually that you should be able to do with this. So we see this come up really frequently on the exam. So first of all, use a given value of delta G to determine if a system is thermodynamically favorable at certain temperatures. Calculate the free energy of the system by applying the summation formula again. Determine thermodynamic favorability by using the going home to supper equation to calculate delta G at given temperature values. And determine the thermodynamic favorability given relative magnitudes, particularly signs, for delta H and delta S under conditions of high and low temperature, okay? Remember also that sometimes you have to convert words into signs. So an endothermic process will have a positive sign of delta H, and an exothermic process will have a negative sign of delta H. A process that is increasing in entropy will have a positive sign, and a system that is decreasing in entropy will have a negative sign. So there you go. That's it for Gibbs free energy, and I'll see you soon for topic 9.4.